he knows what it is. It's a certain age. You have to be more than 20 years old to know what that means. All right. Okay, so this is based on a bunch of papers, starting a long time ago and continuing, just until a few weeks ago. And let me just thank my collaborators, in particular, Eduardo Grossi, who's one of the organizers, who was there since the very beginning. Okay, so so let's first talk about chiral symmetry and heavy ion collisions. So in a limit of two massless flavors, there's a restored phase where chiral symmetry is restored, and then there's a broken phase where chiral symmetry is broken. The order parameter is this SU2 left cross SU2 right symmetry, chiral symmetry, which gets broken. Okay. So in the limit of massless quarks, this would be a second order phase transition, right? But if you have a mass, then it's not exactly a second order phase transition, but a crossover. Okay, and so now, although this is the picture of the phase diagram, okay, we actually have completely ignored the broken chiral symmetry to first approximation in the hydrodynamic description of heavy ion collisions, okay? And so this talk will try to bring that back, okay, into the hydrodynamic description. Okay, so just to sort of set the stage, maybe we sort of remind everyone here, like, what exactly is a pion, okay? And so, well, okay, the order parameter in QCD is like Q bar Q, where Q is U and D, and Q bar Q then is this little like 2 by 2 matrix, which is the diagonal, right? And sort of the order parameter is this little 2 by 2 matrix. And then if you are in the cold world and you have a slow modulation of this phase of this 2 by 2 matrix, multiplying these, quark flavored, rotating these U and Ds amongst each other, okay, that will lead to a slow rotation of this chiral condensate. And the pion is the phase then of this order parameter, okay? It's sort of, this SU2 matrix, okay? And so, of course, in the high TC, above TC, there's no vacuum state. It's not a magnet at all. Okay, it's just some random directions. And then, of course, there is no pion. The pion is propagation is frustrated. Okay, and so, well, in this talk, we're going to sort of ask what happens when you go from this high temperature phase instantaneously to this low temperature phase in a kind of quench scenario, like where you sort of start above TC and then you quench below TC, okay, instantaneously. And we're going to sort of work out the dynamics of how the pions propagate, how they grow during this quench scenario, okay? And to keep sort of maximal theoretically simplicity, we'll start in we'll only do the chiral limit in this talk, okay? So it's sort of not the real world, okay? In the real world, okay, it's not a quench, nor is the pion massless, by far not, okay? So this is really a theoretical exercise. Okay, so let's just sort of say what we sort of expect though. So the quench scenario would be you start above TC, TR is the reduced temperature, right? It starts greater than 0, and at time t equals 0, we go from positive TR to minus TR, okay? And that's the quench scenario that we're going to consider. And of course, just a sort of qualitative picture, above TC you sort of have these random arrows, okay? There's no direction to the chiral condensate or anything like that. And then below TC, you have to make one uniform domain, but you don't really know which domain you should be in. So you sort of produce this random directions, which sort of have to merge, and they grow over time to make one sort of global domain of chiral condensate. Okay. So this was studied a long time ago. It goes by the name of disoriented chiral condensate, but I think there's a lot more to say and to reanalyze and to figure out, okay? So, and in particular, like what happens to the pion spectrum during this quench? scenario, you're making all these domains. The pions is sort of the sort of wavelengths of those domains and what happens to them. Okay, so as I said, it's not about the real world, but let's just say a few words about the real world. Okay, so real world QCD, is a wonderful place. Okay, and what people have measured on the lattice with like gazillions of computer hours. Okay, really gazillions. Okay, is they've measured the fluctuations in this magnetization. Right, so we sort of had this picture of QCD as being below TC as a magnet. What they measured was sort of the fluctuations in the order parameter, the chiral susceptibility, which is the expectation value of sigma squared minus sigma squared. So just let me just set notation here. So the order parameter is this has a magnitude and a phase. The magnitude is what they're measuring on the lattice, and the phase is the pion field. Okay, so what you see here, right, is this is the real world where the pion has a certain mass. That's the green line, okay, and sort of, shows a certain amount of fluctuations. As you make the mass of the pion smaller and smaller, even below the physical point, the fluctuations in the order parameter get larger and larger, okay, and that's indicative of a second order phase transition, okay, so this is somehow the fluctuations in the magnetization. And what's particularly striking about the lattice results on the fluctuations in the magnetization is that the way it increases and it moves to the left in a very characteristic way. Okay, and in fact, that way it moves up, the amount that it moves up, and how it moves to the left is sort of a universal curve. Okay, which is governed by O-Ford scaling. Okay, so somehow the way this increase shows that somehow the real world QCD knows about the O4 critical point or the presence of the O4 critical point. Or it could be a universe different, but right. Okay, but I will take the view that it's O4, which is I think the most conservative, right? So if that fluctuations in the magnetization is governed by like an O4 magnet, okay, or SU2 left cross SU2 right symmetry, then you can write down an O4 simple O4 model, and you can simulate it on almost on your laptop, okay? And so it looks something like this. So the O4 order parameter would be this 4 scalar fields, and it would be called the sigma and the pion, okay? And the Q bar Q, which is sigma e to the I tau pi, is related to these O4 fields. Like if this is a small number, you expand this out, okay? And these parameters of the sigma and pi are related to the sigma and the phase phi, okay? That appear there. Okay, so then if you have this O4 order parameter, you would write down free energy or Landau-Ginzburg function for the O4 order parameter would look something like this, okay? And so in the simulations, you would choose some value of the coupling, okay? Whatever you like. I think we chose 1, okay? And then you would dial this mass, right? Until on the computer until you find a critical point, okay? And you do this numerically, okay? And so you find a number that we call MC, okay? And then you have, if you're close to this critical point, okay, you would identify the difference between this parameter with T minus TC. Okay, so then this critical model makes sort of very definite prediction for how the magnetization should go, okay? In particular, so this is what you can do on your laptop basically, right? I mean, you simulate this model for different values of the mass, okay, and also the magnetic field or the quark mass, okay, and you make a prediction for how the susceptibility should go. So here, this little h is proportional to the magnetic field in this O4 model, and the reduced temperature is m minus mc. Okay, and you find this scaling prediction for how the fluctuations of the magnetization depend on T minus TC. Okay, and so if you actually simulate this on on your laptop, you will find these curves for showing exactly how the fluctuations in the magnetization depend on the quark, the magnetic field, and also the reduced temperature. Okay, and so you can just take this curves, which were found a long time ago, and you can go like plot them on the same scale as the lattice. Okay, and you can see that, okay, right? I mean, it sort of predicts exactly like how this should increase, how the maximum should move to the left, and so on, okay? And so that's a, kind of parameter-free prediction for gazillions and gazillions of real-world computer QCD hours, okay? And I find it amazing, okay? It's universality, it's at its best, okay? And so that's a thermodynamic description, and you'd like to sort of go and have kind of a hydrodynamic description, which would match this thermodynamic description and probably work about as well, okay? It's also a classical theory, yeah. So, of course, these data were from 2019, and it's not trivial, by far not trivial. The left side, this one was done in the 90s originally, and then very much improved in the early 2000s, right? And so, yeah. I mean, this took a zillion hours, right? And still, was only very recently, I mean, right, really many zillions. Okay, that's right. Let's keep in mind that. Right. So, I mean, the physical quark mass was only, I don't know, 15, maybe 15 years ago, right? And so this is even below the physical quark mass, right? So it's non-trivial. Okay. Yeah, it's so for, I mean, let's say these curves were numerical calculation. I mean, originally they were done on a cluster in like the late 90s, but now you could probably fight it through on your laptop if you're a professional, right? Okay, right. Okay, so now we want to go from thermo to hydro, okay, and work out the hydro theory. And one could hope that the hydro theory, which is, I mean, all of this O4 scaling is a classical theory. And one could hope that the hydro, which is also classical, could work about as well, okay. Um, okay, so now when you talk about hydro, okay, Um, you have, again, the order parameter. Okay, so first, what are the relevant degrees of freedom? So first, you have the order parameter, this same order parameter that we had before, this O4 field, sigma and pi. But now when you talk about hydro, you should also include like all of the conserved quantities as well into your hydrodynamic description. And, that would include energy and momentum and all the conserved charges. And it turns out that, energy and momentum is not so important because the critical exponent of specific heat is negative in O4, and the real relevant quantity is actually this conserved isovector charge and the isoaxial vector charge, right? So this isovector charge is basically, isospin, u minus d, right? And the isoaxial vector charge is u left minus d right plus d left minus u right, okay? Neither of which are anomalous, it's all fine, okay? So just have these conserved charges, okay? And you would take these two isovector charges and you would combine them into an O4 multiplet antisymmetric tensor NAB, okay? In much the same way that you combine E and B into the electromagnetic field strength F mu nu, okay? It's actually the algebra sort of equivalent, okay? So you combine these two into this O4 field, NAB. Okay. Now, the thing is that because of the symmetries, like the O4, this conserved charges, generate O4 rotations, right, in this way. Okay, and you know that these charges are the generators of rotation, so that sort of dictates, like, if there is a classical hydrodynamic description, what the Poisson brackets between the conserved charges and the order parameters need to be. So the rotation, O4 rotation group sort of dictates the structure of those Poisson brackets. Okay, and so now if you then want to write down the hydrodynamic description, you would start with the free energy that you had before, okay? This sort of O4 fields, and you would add to it this, as a Gaussian field, the conserved charges. And this chi I is the isospin susceptibility, okay? So that doesn't change the thermodynamics in the slightest, okay? The distribution function is the same as before, right? It's just some Gaussian variables. But it does significantly change the hydrodynamics, because if you start looking at the equations of motion by computing these, Poisson brackets, these things, this phi and this n have some non-trivial Poisson brackets that determine the dynamics. Okay, so if you started with ideal hydro, you would just have this sort of ideal-like equations of motion, non-dissipative. But then you would start adding dissipative corrections and noise to this hydrodynamic description, okay? And it would look something like, it turns out to be highly constrained. I mean, to have only sort of two coefficients, one of which is the conductivity, the charge conductivity or the isospin conductivity. And the other one is this dissipative rate, which records how the order parameter relaxes to equilibrium. So if you make a small perturbation of psi bar psi, how long does it take to go back to equilibrium? Okay. I mean, here in action, no, that would, there isn't. You could add it, but it would sort of say be like near the critical point. This would be some higher derivative operator that shouldn't be changing the critical dynamics. Yeah, yeah. I mean, so it doesn't change the critical dynamics at all, right? Sorry, changes the critical dynamics. It doesn't change the thermodynamics at all, right? It's just a Gaussian charge that you can just integrate out. Okay. Okay. So just writing this out a little bit more explicitly, if you look at the equations of motion, it's sort of this charges, they're coupled to this order parameter, which carries some of all the, make a charged current. And then there's a diffusive part and noise. Okay, so in the high temperature limit, this term is not irrelevant, instead of, there is no order parameter per se. Okay, and you just have a diffusion equation of U's and D quarks. Okay, so in the high temperature region, you just have diffusion of left-handed U's and right-handed U's and left-handed D's and right-handed D's, okay? Okay, and now, but below TC, this term becomes very relevant, that's the order parameter, and it has its own equations of motion, which is sort of somehow a precession equation. The charges cause this field order parameter to precess. It is the Josephson, it's non-abelian like Josephson constraint, right? Right, it somehow says that the time derivative of the phase of this field phi is related to the chemical potential. Okay, so it's a precession. You see, it's kind of, if I drop this dissipative term, it's a precession of equation. It's just saying how the phase is rotating. Okay, so this theory sort of captures sort of two limits. The first is sort of like simple diffusion above TC of the charges. And the second theory below TC is sort of this non-abelian superfluid dynamics, the superfluid modes being the pions, okay? Okay, so let's go a little bit into that. So of course we simulated this. I won't go into any of the details, but we simulated it on lattice and sort of measured all kinds of things, okay? Been doing this for a while. So I will just sort of kind of quickly summarize some of the simulations we've done. Okay, first in the box. So first, per completely equilibrium dynamics. Okay, just sit there forever running the code in the box. Okay, the first thing we checked was that we did no harm. Okay, so we reproduced all of the like static properties of the O4 critical point, like the static exponents, the susceptibilities, all of this stuff, all of this curve that you saw at the beginning of the susceptibility, we reproduce it. Okay, so but I'm going to go through it because it also helps us to set notation. Okay, so let's just review some notations here. So we define here the order parameter is the integral of this thing, okay, over our spatial lattice, M. Okay, magnetization, that's the choice. Okay, and okay, so the mean magnetization or the chiral condensate is this definition. Okay, it's the average of M. Okay, with a very small magnetic field, and it's supposed to scale like the correlation length to specific critical exponents. Okay, or the reduced temperature like T minus TR to the power beta. Okay, and so as you see, like, okay, these are our points, and you can fit it here, and with the right exponents, and with enough work, it really agrees. Very high precision. Okay, even just 1 or 2% in the exponents, and the data points actually have just very, very small percent level, even sub-percent level. I mean, I say how we did it, right? You have to do that very carefully to take the limit that magnetic field goes to 0. We do extrapolate. Actually, we somehow, okay, let's talk about it offline. I mean, let's kind of, of course, you can, and we will be talking about finite wave number. So of course you can take a Fourier transform and measure this order parameter. It's function order parameter, okay? Of course, another thing you could measure here is the susceptibility. So this is the magnetization. And one thing you can measure is the fluctuations in the magnetization, which is what we were chi sub m, which was what we were talking about in the beginning, except we dropped the m now, okay? So the magnetic susceptibility, or chi, okay, not the charge susceptibility, there's two things, is the fluctuations in the magnetization, and it's supposed to scale like c to the 2 minus eta, where c is the correlation length, and we can see divergence of the magnetic susceptibility near the critical point. Okay. Finally, that's all like static quantities. Although it looks okay, it's very poor compared to some people, right? What we have going for us is that we can study real-time dynamics of the process, and our real-time dynamics should be pretty good. Okay, and so one of the first things we looked at was sort of say, just start above TC, okay, and ask how long it takes for the order parameter to reach equilibrium. So you just start evolving and see how long it takes. And so one of the things you could measure is, this integral. So if you think that the order parameter decays exponentially, you would define tau r as being this, this quantity, okay, this integral. And, the expectation is that this will scale, this relaxation time will scale like the correlation length power zeta, where zeta is some exponent known as the dynamical critical exponent, and turns out to be d over 2, or known to be d over 2 for the O4 model. Okay, and so one of the things we did plot was this dynamical critical exponent and fitted, and you can see a d over 2 scaling exponent for the relaxation rate of the order parameter. So again, the notation here is quite important. Tau r is this dynamical relaxation time. It's kind of universal thing. You can measure it lots of different ways, this scaling. And I think we measured like 4 ways, okay? This is just one. The numerical procedure, I think I sketched. I'm not giving in any details, but I sketched. We solved this thing on, right, on the lattice, right? Just solving that thing, and we worked hard. And solve that thing, and I, that thing has the property that it will evolve to this equilibrium configurations, right? And that's what we did, right? And we sit there for, 100 days measuring the same thing, okay? And then after 100 days of, and, a couple hundred gigabytes, okay, then you get M of t for 100 days, and you can then measure this correlation function. It's not Monte Carlo time. It really is physical time. It's physical time. That's the thing that we do better than, like, it's not Monte Carlo time. It's physical time, right? And it's really the hydrodynamic equations with the right physical time that evolves in time, right? And we measure it, right? I mean, right. I mean, we actually start with any variety of, it thermalizes in some, of this 100 days of computer running, it thermalizes in the first 10 minutes, okay? And then you, right, and then you eliminate that from your data sample and measure the rest, right? Yeah, it's really equilibrium, right? So it thermalizes, and you have to check that, right? And of course, you want to verify that it's independent of what initial condition you started with, right? So of course, you can start with a cold start, you could start with a random start, you could put it 0, everywhere you start, however you start it, you always get the same sequence at the end. D is 3 over 3 halves, so it's not analytic, right? Okay, so that's sort of above TC, where you just have simple diffusion, and you just have this simple exponential relaxation for the order parameter. Not exponential, but it's simple sort of blah. Okay. Below TC is much more fascinating subject. Okay, because then you have the order parameter. Okay, and it makes something, and then you get a very rich hydrodynamic theory of pions below the critical point. Okay, so I'd just like to review here the theory of these pions below and the superfluid dynamics below TC. So you look at very long wavelengths. So of course the wavelength of your pion is much larger than the correlation length, which is also large. Okay, so and of course in that limit, it's still much larger than the correlation length, so you can use hydro. It's perfectly valid. Okay, and so naively you might say, okay, if the wavelength is really long, okay, then I even drop the dissipative terms, okay, and so my equations of motion for my order parameter and the conserved charges are these ones, right? So the charge conservation that we had and this Josephson constraint, okay? Now, now you're well below TC, so somehow the magnitude of the order parameters is fixed, right? Sort of equal to the VEV, okay? But the direction of the order parameter can rotate, and that's the phase, okay? And so the hydrodynamic theory is really a theory for this phase, okay? And so, if you treat the magnitude of phi as being fixed, and the direction or spin just fluctuates, so phi a is just a number, f times a spin, which is normalized to 1, then you describe how the spin waves propagate in this below TC, and it's that propagation of those spin waves that is your hydrodynamic effective theory. Okay, and so if I, replace my phi a with f times spin wave, I get a theory of spins and conserved charges. Yeah, just 1 second. So, and basically this is like the hydrodynamic superfluid, non-abelian superfluid theory, just involving phase and the conserved charges. Okay. So then you could just look at these equations and you can solve, right, for the waves that propagate there by linearizing the analysis, and you can find that predicts spin waves which propagate with this speed of f squared over chi I. Yeah. Right. 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 That's all. Okay. So, you can work on improving this sort of 1 slide derivation of the hydrodynamic equations. Okay. but that's the best I can do in one slide, okay? So it's sort of this non-abelian superfluid. It's nonlinear because of this constraint, because SA is 1, okay? And it's sort of, yeah, non-abelian, whatever. Yeah, so it's like, so so NAB is an antisymmetric rank 2 tensor, okay? And you have the isovector charge and the isoaxial vector charge, okay? And so they're like E and B, okay? And you combine the E and B to make FAB, and that's what's in there. So you think of the isovector charge would be like B in our notation, and the isoaxial vector charge would be like E. Yes, and I tell you that we divided Fij, Nij should be isovector charge. Okay. Yeah, I mean, so it is because, I mean, it depends on which way the SA is pointing. Like it's only like defining which one is vector and which one's isovector and which one's axial vector depends on the direction of this S, right? So, and in the real physical world, you'll have a quark mass which picks one, but in the chiral limit, the only thing that can determine it is S, S itself, magnetization. Right. That's right. So if S points in the Z direction, say, then only N0I is coupled to S, right? Right. Right. Good. So, okay. So, of course, we measured this thing like crazy. Um, again, the same 100 zillions of days of running this same code in equilibrium. And then you can measure all of these Pine waves. You can measure how they depend on the critical point and so on. And you can see all that stuff. And so if I go forward, so we can just measure in equilibrium this phi A, okay? Again, equilibrium, non-equal time correlation functions. And, far from TC, you see a really strong Pine wave, which has many, many oscillations, okay, for fixed wave number. As you get closer and closer to TC, right, the waves become increasingly damped. There's increasingly more dissipative corrections, okay, as you get closer and closer to TC, until you finally really don't have a Pine wave at all. And so you can sort of see the transition here from at fixed wave number, you can see from far from TC to close to TC how the Pine begins to emerge. Okay, so of course you see here very clearly a pole frequency, right? A frequency, right, that you can read off, okay, with enough fitting and playing, and so you can fit this dispersion curve, which should have this form of omega as VK, and you can fit this. And what you get from the critical theory, I mean, this comes from any superfluid theory, what you get from a critical theory is essentially how these parameters, like the velocity, like the Pine width, how they depend as you approach the critical point, okay? And so here's a fit to these curves, okay? And there's a scaling prediction for exactly how this velocity should approach the critical point. And, it does work nicely the way it should, okay? Now, okay, so what does the critical scaling tell you? So we have this, we extracted the dispersion curve. The scaling dictates how the velocity and the damping coefficient scale, right? So here's the dispersion curve of VK minus I dAk squared, okay? And so what this critical scaling tells you exactly how these parameters depend, right? So if you have a correlation length C and a relaxation time tau r, okay, then this velocity, which is distance over time, scales like C over tau r. And so if we look at this previous slide, the fact that this goes like this in a very known way, it's just a statement that the velocity scales like this correlation length by the relaxation time just by the dimensions there. Okay, and similarly, the diffusion coefficient or the damping rate of the pions near this critical point scales has the units are distance squared over time. That's like all diffusion coefficients. Okay, and so it scales like the correlation length squared divided by tau r. Tau r still scales like c to the d over 2. So you get some sort of what you get from the critical theory is some sort of non-trivial predictions for how the parameters of the hydrodynamic theory depend as you approach TC. Okay. Okay, so if you have a pion which has a long wavelength L, okay, much larger than the correlation length, then there's going to be a hierarchy of scales. Okay, so if you have this distance, you have one time scale, which is L, the distance divided by the velocity, and that scales like tau r L over c to the power 1. Okay, and if you have a whereas diffusion time, how long it takes to destroy the pion, scales like L squared over dA, which goes like tau r L over c to the power 2, right? And so if L is much larger than c, very long wavelength pions, okay, you have a real distinction between the propagation time of the pion versus the damping time of the pion. Okay, yeah. How I, okay, so this is definition, okay? First one is definition, right? So here's my extracted dispersion curve. It's definition, right, practically. I mean, it's saying that at long enough wavelength, I will have hydrodynamics, and I can measure these dispersion curves very precisely, and I can determine this parameter V and dA. Yeah. True. So it's true. So I mean, there's some overall constants, right? So we just predict the scaling with tau r and c, and there's one overall microscopic time scale, which would be, set to 1, and actually these curves. No, I mean, of course, for numerical, no, we'd basically no. The answer is no. I mean, there's some overall normalization, which is about 1. Okay, very nearly 1. I mean, we do have the numbers in our paper. They depend on like lattice, sort of, we chose our lattice units to be 1. And so then you get some physical numbers out in front, which would be like 1.1, okay? So there's some overall definition of xi, overall definition of tau, okay, which have some constants in front of them, which depend on like order 1 numbers, right? And so, we choose some lattice units, which are 1, right? But at the end, we've tuned ourselves to the critical points to measure times of thousands. I mean, this is thousands, like many of our lattice units, right? And so, and it's that scaling from, although you would have expected, if you're naive, you would have expected a relaxation time of order 1, because we tuned ourselves to the critical point, we're actually getting relaxation times of thousands, right? And that's where, and it's somehow the change from 500 to 1,000 that we really predict, right? Right. Okay. So yeah. So so we have this theory of pions. There's this separation of time scales. So if you have a pion of wavelength L, okay, there's a ballistic time L over V and a diffusion time L squared over D. And they have this scaling where tau r this ballistic time is tau r L over c, and the diffusion time is tau r L over c squared, okay, which is long. The chiral limit, chiral limit, chiral limit. You can, and we probably will, and we have actually already to some extent. But here, to keep it simple, chiral limit, okay? So now let's go back to the problem that was sort of the intro. Now we go back to the real problem of interest here, which was this quench. So you start above TC at some high temperature, and at T equals 0, you go to below TC, right? And then you have to, this condensate needs to grow. And now we have the right dynamics and the equations written down to sort of monitor this growth, okay? And so a very natural and notation, okay? So a natural thing to look at is just sort of say this m squared as a function of time following the quench, right? So at T equals 0, you flip this and you monitor this m squared as a function of time, okay? And with our conventions here, if m is sort of random or short range, relatively short range correlations compared to our box size, okay, then this will be of order 1. And if m is uniform through the box, which is the ultimate equilibrium limit, okay, this will be of order v. Okay, so let's just phrase that out a little bit. You know, so this was the quantity we're going to look at, g naught, or the average of m squared. Okay, the initial conditions at t equals 0 are determined by equilibrium at time 0, okay? And not just saying this is the susceptibility. Okay, it scales like c to the 2 minus eta, independent of volume, okay? But at the end, okay, as the condensate grows, right, m approaches a constant and g naught approaches v sigma squared over 4, okay? The 4 is convention, okay? And it scales like L over c to the power d with this power c 2 minus eta. So we have to somehow, in the whatever dynamical process, we got to go from there to there during the formation of the chiral condensate. Okay, so let's sort of look at it. Okay, so we have this numerical curves. So I will show, let's just sort of, these are the results here for how the chiral condensate grows as a function of time. Okay, and let's just look at it a little more precisely. Okay, so we make these quenches. Okay, so these are different temperatures of the quenches. You know, this is a big jump, a smaller jump. Okay, and then you have these different curves, which are nicely color correlated so that you can see them. Okay, so here's the red jump, okay, there's the orange jump, and you can see how the condensate grows as a function of time, okay? Okay, so of course you would like to have a scaling theory for exactly how the chiral condensate should grow as a function of time, right? And you have a lot of tools like dynamical critical scaling to analyze how this thing should grow, okay? And so in particular, if you use the scaling hypothesis, like all times should be measured in units of this tau r, which scales like c to the power d over 2, right? And all lengths should be measured in units of c, okay? And so, well, okay, so a naive application of dynamical critical scaling would say, okay, the following, you know, if this is function of 3 parameters, but it's actually a function only of these ratios, okay? And then you say, well, I'm considering like super large volumes, actually large compared to the correlation length, right? So if you were a super naive guy, right, you would say, well, this is 0, right? So I should just put it 0. And then I have just a function that says this function should depend on this in this way on a function of time, okay? And so we plotted this function as a function of t over tau r, hoping to find a universal number curve. And of course, what you see is that it doesn't sort of give you a universal curve except for very short times, okay? So at short times, you do see a good data collapse, okay? These are very different simulations, and you see a nice collapse at short times. But at late times, it doesn't show data collapse anymore. And you could ask yourself why, okay? And so, well, it's neglecting terms which become important at late times, right? Which for t of order tau r L over c, okay? And so, well, in going from here to there, we drop those terms, okay? And so we gotta like analyze what happens at late times in this sort of secular regime, okay? And of course, it's not a surprise what happens in some sense, okay? So we were interested in large volumes, L over C much greater than 1, and in the scaling. And we're interested in late times, T much greater than tau R. But the times that we're interested is the time it takes for the pion to propagate across the whole box, right? So the time that we're actually interested in is T of order L over V, which is tau R L over C to the power of 1. So you want to redefine your scaling ansatz to take into account this sort of regime that you're actually interested in. So instead of doing what we did before, we start the same, right? We say this is a function of T over tau R and C over L, right? And now we just reshuffle the parameters to put in all the limits that we know. So at late times, we know this needs to grow like L over C to the power D, right? And we know that the times that we're interested in is kind of L over V, okay? So going from here to here is kind of a trivial rewrite, if you like, okay? Informed, but still trivial, right? It's just sort of reshuffling the parameters into some new function. And then you say, well, okay, now that I've done this sort of rearrangement, it's probably okay, at least for times not super late, to drop this dependence like C over L. And there you get a very simple scaling form for exactly how the chiral condensate should grow as a function of time and the box size, okay? Of course, if you look at early times, you can expand out this thing, then you lose the dependence on the volume and you get a prediction for exactly how the chiral condensate should grow following the quench, okay, as T to the power D. Okay, so of course, I wouldn't be saying all that if it didn't work. So here's the chiral condensate as a function of TR, okay, you rescale the axes, okay. These are different temperatures, and you see how you get a pretty good collapse here for different values of L over C. Okay, good, right? Right. So the residual differences are actually kind of understandable as additional finite size corrections. Okay, so we believe that if you increase the volume further, you would get a universal curve. Okay, and so of course, if you wanted to check here, we changed the temperature, keeping the volume fixed. But you could also check the scaling in alternative ways, like keep the temperature fixed and change the volume, right? And those are very different simulations, okay? And so you could, if you compare these two curves, you see you get the same result, which is another indication of critical scaling. And if you rescale the axes in the same way, you see sort of a similar data collapse, showing like the details of how this data collapse formula work. Okay, great. So that was the chiral condensate, and now we got to go talk about the pions, right? Which are this order parameter and do what they do, right? And so here you need some physics, okay? Oh, I wanted to say one more thing before I go there. So let's ask what this regime corresponds to, okay? So I would argue that this regime of chiral condensate growth is determined entirely by the superfluid theory. In fact, the ideal superfluid theory of the dynamics. Okay, and here's the argument. I mean, so the picture was that you started with this chiral condensate, made a quench, then you have domains which grow in time like VT, right? And after a time which is large compared to the tau R, okay, this size, VT, is much larger than the correlation length, okay? And then the subsequent growth in that regime, right, that's a regime of the superfluid hydro, not the full critical theory, okay? And so, furthermore, okay, dissipation in this growth of the chiral condensate is actually not important because the time of interest is T over L over V, is this ballistic time, tau R over L over C, which is much less than the diffusive time. And so in this regime, you can sort of neglect all of the dissipative dynamics and just use the ideal superfluid hydro spin equations, nonlinear, it's fully nonlinear, okay, and dissipative, but non-dissipative to predict this growth of the chiral condensate. Okay. So if you go now to the pions, okay, so let's look at this picture, which sort of shows how this chiral condensate is growing, okay? So, well, looking at this thing, and let's look at finite wave numbers now. Okay, so the first thing you see is the distinction between like the components, like the zero direction of the scalar field or the one direction of the scalar field, irrelevant here. I mean, like the distinction between sigma and pion, irrelevant, okay? They're all the same, right? Parametrically, I mean, they could differ by factors of order 1, but parametrically they're the same, okay? And furthermore, if you look at the k=1 mode, right, from the k=0 mode, also the same. Like the growth of k=1 is like the same as k=0, okay? And so basically, if you predict a scaling for this, for the magnetization that we argued, right, you expect a similar scaling for the pion, maybe differ by a factor of order 1, but the same scaling form, okay? And so the naive thing would say that g pi pi, right, which is the equal time x pion expectation value, should grow like this same scaling form, like L over c to the d times a function of VTK and KL, right? And now if you then take the limit though, okay, that KL is much, much greater than 1, right? So the box now is super large, but K is finite, then it should become independent of L, right? And you basically get a prediction for how the pion yield, or the equal time expectation value, should scale with the correlation leg and the wave number, and it scales like k over c to the power d times some function of VTK. So it's a pretty striking result, is that if you believe, if you follow that, then you actually find that the way the pion spectrum reaches equilibrium is quite different from other particles in the sense that it would go like this, like it will start at order 1, it will go up to this non-equilibrium regime where it's like take c to the d, and then very slowly, okay, on a much longer time scale, right, it will decay back downward towards equilibrium, which is 1 over kc squared. Yeah, I think that's a coincidence. But okay, whatever. So you get this funny, 1 over k to the d. All right. So okay, so just to say, so this actually works. So if you look at this equal time pion yield following the quench, again you see these nice color coded curves. Okay, and so this is g pi pi over g pi pi equilibrium. G pi pi equilibrium is 1 over kc squared. So you see a very strong enhancement over equilibrium before a slow decay back down to equilibrium. Okay, and well, that's a small number. These are, the smaller is kc, the larger is the enhancement. If you rescale out, if you multiply by kc, then of course you could reproduce it on a common plot, which was this 1 over kc to the d. Okay, so you see a sort of pretty good data collapse. It only should collapse here at very late times, then dissipation becomes important. The final approach to equilibrium, you should expect deviation of data collapse. Okay, so of course you could check this scaling. So we have this kind of prediction for how the pion yield should go following a quench. Okay, and you could check it in a variety of ways. So here we change the temperature, but you could also change the volume, change the wave number, and keep the temperature fixed. And you can see basically it's very similar data collapse, right? Verifying the basic outlines of that. So to summarize then about what you expect, right? You sort of expect at least following a quench, if you calculate the pion yield, that would be essentially what I'm computing, right? It's sort of g pi pi times a factor. And instead of getting the equilibrium one, which is 1 over k squared, you get a 1 over k to the d, which is 1 over k cubed. So you expect an enhancement, which is 1 over k, right? A parametric enhancement. Now, if you have a finite mass that cuts off this growth, right, and instead of getting an infinite enhancement, 1 over k, right, you get an enhancement which is 1 over the mass times c. So you somehow expect that the way pions will reach equilibrium is quite different from other particles. They will get enhanced, right, to a large value, which is enhanced by 1 over mc, and then very slowly, over a long time scale governed by the pion mass squared, right, which I think is a long scale in heavy ions, okay, is it will slowly decay back to equilibrium. So my guess, I think that, you will produce an enhancement and it will then like basically live there to freeze out, okay, for this soft pions, okay. So, okay, so, yeah, so let's say in this context, it's a statement that, let's imagine these are widely separated. So then what would happen is you go up to this region of 1 over kc, and then it would stay there for a very long time and slowly, in this case, you never freeze out, but it would only slowly decay to equilibrium, very slowly. So the yield, G pi pi, is basically the pion yield, like it's that square of the pion wave function, right? It's like the power in that field, right? And so somehow the yields, we can make this more precise. We know how to match this to Boltzmann equation, right? But essentially it's, if you multiply by 2 omega times G pi pi, you get omega being k for massless particles. 2k times this G is the yield, right? Yeah, so I mean, it's a subtle argument, okay, but basically, it's not an easy thing. I agree, right? So the condensate has to grow from something of order chi to something of order v, right? That's what a condensate is. And the pion is essentially part of the same multiplet as the chi, right? So it also goes to something of order v, right? And now you replace v with 1 over k to the d, right? 1 over k cubed. And that's 1 over k cubed is larger by a factor of 1 over k than the equilibrium, right? So essentially it's saying that this is the order parameter. The pion is effectively like order parameter, behaving like the order parameter, right? And so essentially this was the argument, and that it's got to go essentially like L to the power D. And now if you take the volume infinite and k fixed, you get 1 over k to the D, right? So that's perhaps like a solid you have G pi pi proportional to the spectrum, right? But you show the dA of the dA pi of the multiplication of the G pi pi. Yeah. And G pi pi is a functional time. Yeah. Right. So which is the time where you? Yeah. So a perfectly valid question. So of course, if we don't have an infinite parametric range, right? So if we were to make our box bigger and bigger and k smaller and smaller, this would just go up and stay up here for a super, super long time and never ever decay. And then, or very slowly decay. And then it doesn't matter where you cut it off, like somewhere in the middle there. Right, right. Now in practice, we don't have such large cake C, and you can see it in our plots. Cake C is a 5, right? Right. And so of course you do see the decay, right? And then you depend weakly on where exactly you cut it off, right? Right, right, right. And of course, here it's even cake C half, right? So then you kind of don't really see this enhancement even, right? It's just a little anemic enhancement, the red one instead of just a. Go ahead, no, please. Okay, so anyway, so that's this thing, basically expecting that soft pions with the wave number KC much less than of order 1, much less than 1, right, should become enhanced, and then the way they approach equilibrium is they enhance and then decay. Okay, if you look at the pion yields, okay, and you look at this very soft pion yields, you find that they don't work very well with hydro, right? And so although like typical pions work fine, hydro works great, but if you go down there and look in the muck there with pions of order the mass, you find that it's bad, okay? And you see generic enhancement. You don't have to look at these ones here, but you can also see this or this. And so it's a generic problem for this hydro codes to fit this ultra soft yields, okay? And it's not simple to fix, okay? Because, I mean, like, you can easily change the yield, that's no problem. No, that's the fit parameter, right? The total yield. But you have to, like, in a very narrow range of momentum, you somehow have to increase the momentum, the yield. And there's no real scale except to do that, right? And you somehow have to say, oh, it's equilibrium up here, and if it's equilibrium the whole way, there's no reason to think that like this would change, right? And so somehow we would describe this somewhat naturally that like in high momentum range, it's an equilibrium, no problem. KC is of order 1. And as you go down in momentum, KC much less than 1, you should fall out of equilibrium and actually be enhanced, okay? And so, maybe this is what's going on, okay? Oh yeah, I mean, the zillions. No, I mean, you can try. This one I don't think does, but this Shea and Gersoy Snellings does, right? Yeah. Right. So that's right. It seems to be the pion specifically, and also just low moment, very low momentum, where you start to see the deviation, right? Yeah. And also you have the mass, right? So you have here mass as well. So you have the mass as well. So it like MT or omega is actually quite a bit larger, right? Right, right, right. Okay, so anyway, so if I can just kind of summarize, I mean, so we sort of wrote down this critical model for critical point. It's like a great model, really a whole lot of fun. Okay, and what's good about it is it almost doesn't really totally need the critical dynamics, to be honest, right? Because it has 2 hydrodynamic limits on either end. Like it has vanilla diffusion of quarks on one side and like pion superfluid on the other. And in between, it does something, right? And you only really need the critical dynamics in between, right? So during the quench, the condensate has sort of generic growth, right? Because it's got to go like L to the power D. And so if you look at the pions, which are also part of the same multiplet, they sort of have to track the same way. And that leads to a prediction for this pion enhancement. What I find particularly wonderful, and if I can, is that this pion enhancement is controlled by this superfluid theory, right? Actually the non-dissipative parts, right? And so actually the parameters of this pion superfluid theory are actually computable. It's like ideal hydro. And because it's like ideal hydro, there are all the parameters like F pi and the mass and so on are computable on the lattice. So there's real hope to sort of like have kind of precise input from QCD to very strongly constrain this dynamics, okay? And if I get, because the pions are attracted to the condensate, they get enhanced, by a factor of 1 over m pi before slowly relaxating to equilibrium. And that's a kind of rigorous statement, right? In the sense of, you know, it's a parametric enhancement, not a numerical one. Okay. And if I can just summarize, sort of give you some kind of picture. So you had some sort of like local correlations here, right? And they are this big, right? And the pion that you're trying to produce, right, is this big, right? It's the size of this room. And so, of course, like the way you go from this small correlation functions to this gigantic one is kind of universal. And that's where this superfluid theory, can do its job and really describe that dynamics with precision. Okay, so I really hope this is what they're seeing in experiment, and a lot of work to fight that through and be sure about that. Okay. I mean, let's, I mean, there's a lot of, I don't want to overstate it, right? But it is seen everywhere, and it's not easy to fix, right? And so you can play with, and we're gonna do this, like, I mean, like all the different hydro models are suffering with this. You mean like star? And if you look at star, look, good question. Good question. Certainly, this the star. Of course, you have to trust somehow the baseline a little bit, right? And so that's. But certainly, you do see the enhancement at star at Rick, right? 200 GeV. Well, but even at Rick and way below, you're well above the critical temperature, right? So I'm not clear that you shouldn't see it at Rick, but even way down in temperature, at really low energy, I think you should still see it, right? And yeah, so I don't have it, but I have only an analysis from 200 GeV, but the 200 G definitely shows it about the same, which is kind of consistent. I guess the question would be, like in PP, I'm not even sure that, like in PP, well, enhanced compared to what, right? Is kind of a little bit of the issue. So maybe looking at the slope change is maybe a better way to. I don't, so you need, of course, you need to, like, for non-heavy ion people, like CMS doesn't measure below this point, right? So like, Atlas, you need people who are very confident in their low PT spectrum, which is not that many, and pretty recent, right? That they're very super confident about these points, right? Um, so so certainly, what, yeah. So I mean, of course, the basic question I think, if I can phrase, is you should couple this model G to some real hydro code, and then you'd be running hydro and model G, and fitting everything, and hopefully do a better job at this low PT pions. No, no, this is a zero baryon chemical potential. So we're really talking about on that at zero, mu B equals 0. So it's not model H, it's really model G, right? And of course, you have a finite quark mass, which tunes you away from the model G, the second order phase transition. So for any real phenomenology, I mean, you need the mass. The mass is like an enormous, parameter that is actually tuning you pretty far from the critical point, right? And I mean, we actually know an awful lot about, I mean, we already know a lot from the lattice about what the real parameters are here, both the mass and the F pi is actually can be known with very high precision. And having talked with the people, I think are going to, basically measure F pi and M very precisely near the crossover and even below the physical mass. So I think in the near future, we're going to know the parameters of the superfluid theory with the ideal superfluid theory with some precision, right? And they actually have measured like sigma mass. I mean, and they know that pretty well, right, near the lattice, and the pion screening mass also known pretty well. So, and with will, and they can actually do a really good job. Right. The dissipative parameters, forget, right? Then we just, but fortunately for the enhancement, you actually don't need the dissipative parameters. And so, um, though for precision, of course, you have to put in some dissipative numbers, right? Um, right. So the, the pole mass goes to 0, right? Um, and the screening mass goes to, we put everything 0, all our pion mass was 0, but that's of course the first next step is just to turn on we can study the mass, how this depends on the mass and the scaling, how this curve depends on the scaling, that we can, in some ways I've already started. For instance, this curve, how exactly it depends on the mass, we can study. Mm-hmm. Of course, no, absolutely. So I mean that puts a whole very serious, just like the pion mass itself is like the largest the correlation length could be, right? And okay, and but of course the enhancement isn't that large either, right? And so I think it's actually good. I mean, like the enhancement, or there's nothing totally nuts down there. Like it's an enhancement that's hard to explain and so on, but it's not like uh, factor 10 enhancement. Okay, it's some 50%, right? And I honestly think that if the pion mass were like 20 MeV instead of 140 MeV, I think all of this physics would hit us in the face and would have hit us in the face a long time ago, right? And it would have stuck out in the detector like 100%, right? Yeah, so in principle, indeed, like the 2 pi and correlation function would be not just the yield, but the 2 pi and correlation function is something you has scaling predictions. Should this scaling regime with this coarsening should also be a prediction. And so definitely like looking at the actual 2 pi and yield correlation function is something we want to do, and it's essential to convince anybody in experiment that this is really what's going on. That's right. I mean, it, in the language of quantum optics, right? People would call the 2 pi and yield the G2 of tau, which would be, so-called second order correlations. And so we should, and then if it's a coherent classical field, it has different statistics compared to, you know, a quantum statistics, right? And so certainly something I'm thinking about is whether you could at least look at that quantum, how classical is it, right? That's something they can do with experiment. And it's a good first step is just to say, is it classical, right? We need it to be classical, okay? And then I hope it's somewhat classical, right? I don't know. I mean, so, it's a pretty local, one thing as people were saying, like, you know, let's maybe keep some sense of scales. Like I said, here's this local correlation length and it's got to grow to the pion that's this big, right? Except in the real world, it's like this big, and which is one, maybe 2 Fermi most, right? 1/m², right? And let's keep in mind that the freeze out volume of a heavy ion collision is thousands of Fermi, right? And so it's extremely local, right? It's like a correction to there's no long, I mean, long range in some sense, but in terms of the actual overall volume of the heavy ion collisions is really very tiny, right? So it's very more like how do you produce the pions that coming from the freeze out surface is more the way you could model it, right? So, So we have already done this for the Kibble-Zurich scenario, where like the temperature is dropping at a steady rate, and you see the basic same feature, right? But of course, the danger is not the real expansion dynamics. The danger is actually more the equilibrium dynamics, right? So if you're going slow enough through the critical point, then of course you're in equilibrium the whole time, right? And then no enhancement, right? But what does slow mean, right? Is not 1/pi_t. It has m⁵² there. So you have to be, m⁵² is 27. So if the typical scattering rate is 1/pi_t, you take 27 times that, and that's a long thing, right? So it's not enough to be slow. You have to be parametrically slow, right? All right.